Hello everyone. Today is the last day of the last week of classes, and what I usually like to do for the last recitation is to just have a sort of an open test review where I ask you all questions, and whatever you come up with, whatever you're curious about, that's the problems that we go over. But of course we can't do that this time, so what we're going to do is go over some of the problems from all three of the previous tests. So first of all, let's look at the first test and the second multiple choice question. So we have a negative charge and a positive charge sort of equidistant from this imaginary line, and there's a point on this line, and we're asked what is the electric field at that point, or rather what's the direction of the electric field at that point. And the choices are A, B, C, and D. A is upward, B is downward, C is to the right, and D is to the left. Okay? And to answer this problem, and recall that, of course, we have multiple choice questions where you can't just circle what you know to be the right answer. You have to reason through it and provide your reasoning also. So let's go ahead and draw the vectors for what the electric field should be at this point. So we know what the sign convention is for electric fields. They do sort of whatever they would do to a positive test charge is the sign of the field at that point. So this is a positive charge right here. You can imagine it pushing a positive charge sort of off that way. So the direction of the electric field at this point is going to be radially away from the plus Q charge. Let's call this, I don't know, E plus. E plus looks good. Okay, now let's draw a line from the negative charge to the point, and then the negative charge does the opposite. If you put a positive charge at the point P, the negative charge right here would be sort of drawing it backward, sucking it backward. So the direction of the electric field at the point P goes back toward minus Q. And let's call that one E minus. Okay? And then the vector sum of those two, the total electric field is going to be the sum of E plus E minus. And if we graphically add these two vectors, we're going to get a vector where the part in the horizontal direction is going to be canceled out because this one's going to be just as long as this one. So, because these are two equal charges, and then all that's left over is the part that points upward. So that's going to be the net electric field. So the correct answer is A, that the electric field points upward. Now let's take a look at number 4, multiple choice number 4. And in this one, we're given a point charge placed at the center of a spherical Gaussian surface. So this problem is going to be much easier to follow along if you have your first test to look at, because I don't really want to list out all the answers, all the possible answers. But the picture that we should be looking at, though, is we've got a point charge Q. We're going to imagine a Gaussian, well, that's not really in the center. There we go. I'm going to imagine this sphere surrounding the point charge Q, where Q is just in the center. And that's going to be our spherical Gaussian surface. Okay, and the answers are, well, the question is the electric flux changed? And the answers are A, if the sphere is replaced by a cube of the same volume, B, if the sphere is replaced by a cube of 1/10 the volume, C, if the point charge is moved off center but still inside the original sphere, D, if the point charge is moved to just outside the sphere, and E, if a second point charge is placed just outside the sphere. So to answer this, we need to think about Gauss's law. Recall the Gauss's law says that the integral about a closed surface of E dot dA is going to be equal to Q inside divided by epsilon naught, or that it's just proportional only to Q inside and nothing else. And that's the form of Gauss's law that we think about most of the time, because most of the time we use Gauss's law, we use it to find magnitudes of electric fields. That's kind of the main utility of Gauss's law. But we can also recall that the net flux through that Gaussian surface is equal to that integral. In fact, that's two ways of defining the net flux put together that makes Gauss's law. So the quantity that we're really calculating in Gauss's law is the net flux. So to answer this problem, let's think about it in terms of Gauss's law. So A, if the sphere is replaced by a cube of the same volume, so if we have a big sort of imagine a cube of the same volume with that charge Q in the middle, and let's think about what the flux is now. So if the flux inside this thing is equal to Q inside over epsilon naught, notice what doesn't show up on the right-hand side of Gauss's law, and that's the shape of the thing. There's no stipulation on what shape the Gaussian surface has to be. So phi net is just going to be proportional to Q inside, and we have the same Q inside with the cubical Gaussian surface. So the flux is the same, and the flux doesn't change. So A is not the correct answer. And B says, what if we look at a cube of 1/10 the volume? And another thing that doesn't show up on the right-hand side of Gauss's law is the volume of the Gaussian surface. It doesn't show up anywhere. So you can change the volume however you like, but the flux through that surface is going to be the same. And so B is also incorrect because volume doesn't matter. The flux is the same in both cases. And I'm going to skip C for the time being because that one's a little bit more subtle to think about. It's a bit more interesting. So we're going to save that one for last. So let's look at D. If the point charge is moved just outside the sphere, so if instead we move Q outside the sphere, well, this time Q inside has gone from whatever that charge is, and now it's 0 because there's nothing inside that Gaussian surface. So this definitely does change the flux. It goes from whatever it was before down to 0 because there's no charge inside. And so the correct answer is obviously D, that if we move the point charge outside of the sphere, then the flux changes. So the correct answer is D. If you're following along, then I'll write that right there. But let's go ahead and look at the other two incorrect answers just for more sort of illumination on the problem. If a second point charge is placed just outside the sphere, I'm going to recycle this just a bit. So we're back to the original scenario where we have Q inside the Gaussian sphere, but now we're going to have another Q, and I'm going to call that, I don't know, Q primed maybe. And we're going to place that just outside the sphere. Does that change the electric flux? And offhand, you might think it does. So if we're thinking about electric flux, we're thinking about all these field lines sort of radiating outward from the sphere. And then there are going to be a bunch cutting through this Gaussian surface from that second charge. But the key thing to remember is that all of the electric field arrows that are entering the Gaussian surface are also exiting. So whatever flux there is coming in is flux going out, and so it just cancels itself out. In the very same way that when we had just the charge outside, there was no flux, no net flux coming through here. If we add whatever charges we like outside, it doesn't change the flux through that surface, only the charge enclosed, which is what Q inside means. And sometimes you might see that written that way also, which is shorthand for Q enclosed. But the charge does have to definitely be inside the Gaussian surface. And then finally, let's take a look at C. I'm going to draw a new picture for C. Actually, we're going to draw two pictures for C. So originally we have, here's our Gaussian sphere, and there's Q. And C says, what happens to the flux if we move the charge Q off center? So we're going to go from the center and move Q like perhaps over there. How about that? Now let's take a look at the field lines. There's a bunch of field lines radiating outward from Q like this. And the very same thing is true for this Q. Okay? And remember, the point charges, their electric fields that surround them are spherically symmetric, right? So in this case, the spherical symmetry of the electric field vectors perfectly matches the Gaussian sphere that we've drawn. And you'll see that each one of those vectors is sort of perpendicular as it pokes out of the surface, and they're all equidistant from each other. The density of field lines is the same at all points. And that's not true for this one. Some of them will be, well, some of them are going to be at 90 degrees, but some of them won't. The angle between the spherical surface and the field lines won't always be perpendicular. And also, more importantly, if you're thinking about the magnitude of the electric field along this surface, you have a greater density of field lines over here on the right than on the left. So the side that the charge is closer to has a lot more field lines coming through it than the spread outside over here far from it, okay? Now, Gauss's law says Q inside is the same for both, therefore the flux has to be the same for both. And so on the places where the field lines are closer together, that's sort of making up for the fact that they're farther apart over here, and you still have the same number of field lines. Loosely speaking, think about that as sort of a heuristic. The same number of field lines poking out of the surface as before. The thing that's different is now the electric field along this surface. We don't have that spherical symmetry anymore, so it's no longer true that the electric field is going to be the same at all points on this sphere. That part has changed. So if you had a question relating to the electric field on the surface of a sphere, that would not be the case. And so since that's changed, it's really easy to fool yourself into thinking something else has changed here too, like the flux is different, but it's really the same. Okay, now let's move along to one of the computational problems. And so let's take a look at problem 2. In problem 2, we're talking about a large, flat, horizontal, non-conducting sheet. So basically a plane of charge. And we have some charge density, some negative charge density on that plane. And we're looking for the magnitude of the electric field at just above the surface of the plane, and also the direction. So here's our sheet of charge. And at this point, you could definitely look at your equation sheet and you could see that E is equal to the charge density divided by 2 times epsilon naught. And you could plug in the charge density, which is given to you, that's minus 10 microcoulombs per meter squared. And then epsilon naught, something that's going to be on your equation sheet or in the back of your book, for example, and calculate that and be done. But let's look at where that formula actually comes from, just for practice using Gauss's law. And if you had a problem that said use Gauss's law to find the electric field, you would need to know how to do it. So let's take a look at that. Remember, the first thing that we do, let's write out Gauss's law. Okay, remember the first thing we do in Gauss's law problems. Where does Gauss's law apply? And recall that Gauss's law only applies for closed surfaces, right? So we have to invent some imaginary closed surface before we can even think about Gauss's law. Okay, and we want to be really clever in the way that we choose the surface so that this integral becomes something easy. So remember how dot products worked, that E dot dA is equal to E times dA times the cosine of the angle between E and dA. So that's just expanding what the dot product means. Okay, and so right here we have this cosine theta term. We have to think about how the electric field relates to theta. Electric field could actually be a function of perhaps the angle or something like that. So we have to think about the angular dependence of the electric field and also how to integrate this cosine theta term. And we don't want to do any of that. We don't want to do double integrals. Because remember, the entire purpose of sort of introducing Gauss's law for finding electric fields in the first place was so that we didn't have to do these crazy multiple integrals to find electric fields for charge distributions. So we want to be clever and find a way that this goes away, the cosine theta term. So I'm going to write this over here. And we want this to go away. The first thing we're going to note is, because it's a very large plane and the electric field vectors are all going to sort of point perpendicular to it. I'm also sort of giving away the fact that the electric field vectors point down, but I mean, it's got a negative charge distribution on it, so a positive charge would be attracted to this thing. So, the Gaussian surface that we want to draw is a cylinder. Well, I've drawn a cylinder, but you can draw any volume that's going to have sort of straight walls and then some kind of perpendicular top and bottom areas. Okay, so we've got this area at the top, and that's A, and that's A. And then we've got this area being cut out of the middle of this thing, and that's also A. Okay? And that's very important. That makes the math easier later on. But let's go ahead and check that this does eliminate our cosine theta term, because we don't want to deal with that. So we have area vectors. Remember that the the area vectors proportional to the area and then point perpendicular to that area. Like something like, if we can imagine sort of a sheet of paper, the area vector pokes out of it, and then its orientation in space is always given by that vector. And that's no different for our dAs, our little differential bits of area. Okay, so they're pointing sort of radially outward on the cylindrical part of this, and at the ends they point perpendicular. They point perpendicular like that. So that the E field vectors right along the surface of the sphere, the cylinder, the cylindrical part, are going to be 90 degrees away from E. We have this arrangement. We've got E, we've got dA like this, and the angle between E and dA is 90 degrees. And what's the cosine of 90 degrees? The cosine of 90 degrees is 0. So all along the cylindrical part of this surface, the cosine theta term is 0, and that means that E dot dA is 0, and we don't have to think about it anymore. Okay? So now let's look at, it's easier if we look at this one, the E field vectors at the ends. Okay? And they're right in line now with the dAs. So E points down, and dA also points down. And there is no angle between them at all. They're right in line with each other, which means that theta is 0. And if we recall that the cosine of 0, rather, is 1, then our expression for the end cap parts becomes E dot dA equals E times dA times cosine of 0, which is 1. So that's just equal to E dA. And also, really importantly, all these E field vectors are in a line, so there's no angular dependence. The electric field has no angular dependence at all. So E is now a constant that we can pull outside of the integral. So if we integrate over the entire area of E dot dA, and E is a constant that we can pull outside, then that's just the integral of dA, which is A. The integral over the whole surface of all the differential bits of that surface is just equal to that area. So that becomes E times A. And this is a trick that you can use in every Gauss's law problem. Find some symmetry in the electric field that you can exploit to make this vector integral just become E times A. By choosing the cylinder, we've done that. Actually, there is one subtlety to this one, though, that I haven't pointed out yet. Ordinarily, it's E times A, and it is E times A. It's E times the area. But in this case, the area is actually 2A, because I've labeled this end cap area A, and we've got flux going through 2 of them. So the E field vectors poke through sort of 2 areas. There. That looks better. So that's actually going to be equal to 2A, since we have twice what this thing is. Twice what A is. And now we write 2EA, and then what's that equal to? Gauss's law says that that's equal to Q inside over epsilon naught. And what's Q inside? Well, we're not given a total charge, actually. We're given a distributed charge. All we know about this thing is that there's some charge distribution, sigma, spread out over the surface of that sheet. How is sigma defined? So if we think about all of the charge distributions, like for example the linear charge distribution, that was a total charge divided by, say, a length of wire, for example. And if we have a two-dimensional charge distribution, that's going to be a total charge distributed over an area. And if we have like a volumetric charge distribution, that's just total charge divided by the volume. Well, that means that sigma is defined by total charge divided by an area. Okay? And what's the area that we're considering? So all the charge that we have enclosed by the cylinder, what Q inside is that charge distribution distributed over this area, the one that's cut out by the cylinder, and that's going to be A also. So that's the same A right there. Q inside is then going to be sigma times A, if we go ahead and solve this thing for Q inside. So we can write that here. Sigma A over epsilon naught. And now we have everything we need because we know A. Well, we don't know A, actually. We could find it easily, but we don't need to. We've got an A on both sides. We know sigma and we know epsilon naught. We've got E in terms of stuff that we know. So obviously, since we have an A on both sides and it's non-zero, we can go ahead and cancel that thing. And we can divide both sides by 2. And when we do that, we get the formula for the electric field of a plane of charge, or a sheet of charge. And at this point, to actually get a numerical answer for your problem, you can plug in your minus 10 microcoulombs per meter squared right here, and then plug in epsilon naught from the back of your book, for example, and get some number. And I'm not going to do that for the sake of brevity, and also because my calculator is dead. But you can do that at home. And this is where you would start with this problem. And if you were asked to show how Gauss's law gets you here, then you could go through this derivation. Part B says, what's the direction of the electric field? And we've actually already discussed this when drawing our picture. But since the charge distribution is negative on the sheet, if you had positive charge just free somewhere above the sheet, it would be drawn downward. And so by convention, that means the electric field is going downward toward the sheet. So just to recap how we got to this place. Anytime you see finding an electric field using Gauss's law problem, write out the equation at first. Start here to remind yourself that you need to find some Gaussian surface that makes this integral expression much easier to deal with. And if you find one such that cosine theta term drops out and the E becomes a constant, exploit some symmetry of the problem, then you can just go ahead and write that integral as the electric field times the area, and you're done. So most of the work is taken care of in our choice of Gaussian surface. And then at that point you can equate that to Q inside over epsilon naught. If you have a distribution instead of a total charge given, then you can go ahead and write out whatever the charge distribution expression is and solve for that to get Q inside. And then do a little bit of algebra to get your expression for the electric field. Okay, let's look at one more problem from test 1. So this one will be problem 3A, and it concerns a non-conducting sphere with positive charge distribution on it. So we have this sphere. The sphere has a radius of 12 centimeters. I'm going to go ahead and draw these also. 18 centimeters and 6 centimeters. And we're asked the same question about the sphere, only at 2 different distances. And the first question is, what's the magnitude and direction of the electric field at that distance, and what is the electric potential at that distance? First for 18 centimeters in part A, and for 6 centimeters in part B. Okay? And again, we won't do this numerically. We're just going to look at, how you would set up the problem and then plug in the numbers. But in any case, there is a total charge given for this thing. So we have total charge. And if we do Gauss's law, go ahead and write that up. E dot dA is equal to Q inside over epsilon naught. Okay? So let's do the 18 centimeters first. Okay, so if we imagine a Gaussian sphere at 18 centimeters, we're going to get E times A equals Q inside over epsilon naught. And Q inside at 18 centimeters, because it's outside of the sphere, is going to include the entire charge of that sphere. So Q inside is just going to be, I guess I'll just call this Q. I need to call it Q total. That's just Q, the Q for the original sphere. Okay? And I got to just write E times A because, just like in the last problem, I've taken advantage of symmetry of the problem. And because this charge distribution is spherically symmetric, I can draw a sphere around it, and all of the vectors are perpendicular to it. The E field vectors are perpendicular to the area vectors. And that means that we can just pull E outside. Integral of dA is just A, and we get E times A. Okay, and what is the area? So the area that we're looking at is the area of this Gaussian sphere. And if you'll recall that the area of a sphere is 4 times pi r squared, A for a sphere is 4 times pi r squared. We can go ahead and stick that in here. E times A is E times 4 pi r squared. And so this is the relationship for the total flux that we got from Gauss's law. And we want the electric field, so we're going to rearrange this thing for E. So we need to divide both sides by 4 pi r squared. And I'm going to write this as 1 over 4 pi, put the epsilon naught in this term, and then Q over r squared. And the reason I've done it like that is to point out the fact that this is exactly the expression you would get for Coulomb's law for a point charge. Which means, of course, that for a sphere, outside of a sphere, if you have a spherical charge distribution, it acts exactly like a point charge at the center with Coulomb's law, which is an interesting, at least I think that's sort of an interesting fact. And at this point, you could go ahead and calculate what that E field is at 18 centimeters. 1 over 4 pi epsilon naught is just our KE that's in your book or on the equation sheet, or calculate it using epsilon naught, that's fine also. Q is your total charge given in the problem, which I think is minus 2 microcoulombs. And then R that you're going to use here is the 18 centimeters. So be careful not to use the 12 centimeters, but go ahead and use 18 centimeters and convert that into meters, and then you should get some number for that. Okay? And then the direction. Well, if I had, for example, a positive charge just sort of floating about outside the sphere, 18 centimeters away, this is a positive charge distribution, so you've got 2 microcoulombs here and some positive charge here. It's going to be repulsive, right, since they're both positive, which means that the E field vectors point radially outward. And so the direction is, you have 3 choices for the direction: inward, outward, and no direction, and then outward is the correct answer. Okay, before answering the potential part of this, let's go ahead and talk about the electric field at 6 centimeters, and do the electric fields together and then the potentials together. Okay, so if we sort of redraw our Gaussian surface, which is at 6 centimeters now, that's inside the sphere. I think I made a mistake earlier and said that this was non-conducting. This is a conducting sphere. So this is like a lump of metal. You can think of it like a metal sort of sphere. Okay, and what do we know about conductors? I mean, what makes them conductors? And so what makes a conductor conductive is that all the electrons are sort of free to flow about inside the material. They're not bound to whatever atom they came from. So as you add more and more atoms, the electrons just sort of break free and make an electron gas sort of thing that can flow freely throughout the material. And because they can do this, if we put a net charge on this thing, if we put, say, too many electrons on this lump of metal, they're going to want to get as far apart as they can. So they don't want to be near each other because they repel each other. So they're going to arrange themselves on the surface of the sphere because that's as far apart as they can get, right? And so the same is true for positive charge. If you put a net positive charge on the thing, they'll do exactly the opposite. And the positive charge carriers that you can imagine are arranging themselves on the outside of the sphere so that all of the net charge is arranged at the surface of the sphere and there's no net charge in the middle. And that comes straight from the fact that the material is conductive, okay? And it wants to minimize it really wants to minimize the potential energy actually, but it wants to minimize the electric field on the inside. So the electric field on the inside, we know it's 0, but let's look at why. So if we do Gauss's law for this thing again, and we've done the same work as before, just written out this expression for E dot dA as E times 4 pi epsilon naught r squared, and then solve that right here. But really at this point we're done because this imaginary Gaussian sphere is not enclosing any charge because all of the charge is at the surface, right? So Q inside is 0, Q inside is 0, and that means that E is 0. And that is the reason why electric fields inside conductors are 0. So you can write 0 in that slot right there because that is in fact the answer and there's no direction for it. But it's instructive to think about why that's actually the case using Gauss's law. And now let's think about the electric potential, both inside and outside the sphere. So first let's do outside. And outside, we get this expression. This is the expression for the electric potential for a point charge, but we know that this thing is behaving like a point charge outside the sphere. We just saw that using Gauss's law. So we can go ahead and write this up there. And that's 1 over 4 pi epsilon naught q over r. And we really do think about potentials as potential differences. The other point would be at infinity. And at infinity, as r tends to infinity, this expression tends towards 0. So that's really, there's nothing to be thinking about there. But if you think about potential energy as a definition of moving the particle in, a particle in from infinity to a certain distance, how much work did you have to put in, then you can think about it that way also. Or you can just write out this expression and calculate that as a number using 18 centimeters for your r once again. Now for part B, it's a little bit more tricky because as we go sort of inside this sphere, we're not picking up any more charge. We're getting closer and closer to the charge until we reach this point at the surface of the sphere. And like we just talked about, there's no charge inside, so it sort of stops. What does the potential graph for a conductor look like? Okay. And it does something like this. It's proportional to 1 over r outside, so this is the radius. And that's the potential, and then it sort of just stops. And you have a constant potential inside. And that constant potential is equal to the potential at the surface. And it's important to think about this because non-conductors don't do this. In a non-conductor, the charge is distributed throughout, and the potential is going to change once you get inside the thing. But at this point, we're sort of inside the sphere. Everywhere inside the sphere, the potential is going to be the same, and it's going to be the value that it was at the radius. I'll say uppercase r. The radius of 12 centimeters. So the common mistake to make here was to use the same expression and plug in 6 centimeters for r. And that's wrong. That's going to give you something totally different than this. That's going to give you maybe something up here. But we're looking for this constant voltage right here inside the sphere that you get by plugging in 12 centimeters for r. So for part B, you should in fact use 12 centimeters in the potential equation.